Welcome to clickmyproject.com.
Now we discuss about the product for area delay efficient binary adder in QCA. Next we discuss about the abstract for the product. Quantum dot cellular automata technology provide a promising appropriate to overcome a approaching limit of conventional CMOS technology. For this reason, in recent years, the design of logic circuit based on QCA has received a great deal of attention, and special effort has been directed towards arithmetic circuits such as adders, multipliers, and dividers. Even though multiplier is our key element for a wide range of application of QCA implementation existing in the literature on mainly provided for comparing two single bits. Only few examples multipliers able to process n bit operand with n greater than 2 are available. Multiplier described as simple computes the XNOR function establishes the whether two input A and B for match for each other functions. Our work to develop the multiplying architecture based on the QCA addition process. Low power issue have become an important factor in modern VLSI design. The limited power capacity system has given to rise to more power aware design by designers. Nowadays, problems have become a crucial factor than area or speed. However, different implementation technologies present different power optimization opportunities. Low power digital multiplier design based on bypassing technique mainly used to reduce the switching power dissipation. While this technique offers great dynamic power saving, mainly in array multiplier and due to their regular interconnection scheme, it misses the reduced area and high speed advantage of tree multiplier. Therefore, mixed style architecture using a traditional tree based path combined with the bypass array based path is proposed. Prototyping of all these multiplier architecture, a digital adder is a hardware electronic device that takes the two number. Adder is used in central processing unit and microcontroller process. Quantum dot cellular automata refer to is to simplify the high performance technology in digital circuits. The binary adder is to optimize the pattern gate count in regular multiplier architecture based on majority gate process. In this proposed architecture, the 32-bit multiplier pattern count is to be optimized based on majority gate architecture and to improve 32-bit multiplier performance. Multiplier play a important role to today digital signal processing and various these application. With advantages in technology, many research have tried to trying to design multipliers which offers their following designs targets: high speed, low power consumption, regularity of layout, and hence less area, or even combination of them in one multiplayer, thus making them suitable for various high speed, low power, and compact VLSI implementation. Next, we see the flow diagram for the product. First of all, the input binary bits are applied to the multiplier architecture. Our design to 16-bit multiplier architecture for output results for 32-bit multiplying process result. The multiplicand and multiplier functions to be added for the using the AND gate function for the partial order generation input. Thus, the partial order generation mainly based on the addition process. The full adder and half adder architecture mainly used for the partial order generation addition unit. So, we implement the Franklin logic function for 3-input majority gate architecture. So we reduce the 3-input majority gate architecture pattern count using the Franklin logic functions. This Franklin logic function is mainly used to modify the Boolean equation and reduce the gate pattern count. Then to design the full adder and half adder mainly based on the majority gate architecture designs. So we design the adder and half adder and full adder architecture and to apply the partial border generation for 32-bit multiplier architecture unit. So the partial border generation mainly based on the half adder and full adder work for 3-bit majority gate architecture and to display the output results for multiplying results. Then we calculate the simulation and synthesis results. The synthesis results mainly used to calculate the area and time allocation for overall multiplying architecture, and the simulation results mainly calculate the circuit process is correctly processed by the multiplying results. Then to check the two processing results and to implement the overall process. So we apply the input binary bits and to multiply the Multiplicand and multiplier functions don't produce the results to apply the partial product generation and to modify the architecture level using the Franklin logic function for our overall processing in our architecture level. Next we see the final output for the product. First we run the architecture for Xilinx ISC project. Just double click the process. Next we open the processing for multiplayer architecture. Our multiplayer architecture was developed in VHL language, and using the structural modeling designs we apply the 16-bit multiplayer architecture. And this 16-bit multiplayer architecture produce the results for 32-bit. Then to select the simulation process and to select the multipliering function, then to run the simulate behavior model. To create the iSim project navigator. This iSim project navigator mainly used to simulate the our 16-bit multiplayer architecture. Just we apply the binary input inputs for 16-bit results and to produce the 32-bit output results. This is our architecture for our 32-bit resulting process. Just we apply the input for binary process. Just we given the 32-bit input for our architecture, 16-bit architecture. Then to produce the results about the architecture results and to apply the given process. Then to run the our multiplying architecture. This is our 32-bit multiplier architecture results, and multiplier multiplication, multiplicand and multiplier operand to be applied the our multiplier architecture, and to these are the signals of overall architecture process. This is the final output for our architecture. This is our simulation result. Then we go to the implementation process. Implementation process to select and to run the view RTL schematic process. Just to double click the RTL process and add and create the schematic diagram. This RTL diagram mainly used to what are the logical blocks placed in our overall 32-bit architecture. This is our multiplier diagram. This is our technology diagram to represent the what are the input and outputs, LUT functions, then lookup tables and the wire connections, input output buffers placement for overall architecture. Then go to the design summary process. The design summary process mainly used to simulate our the overall processing results and to produce the binary results, then to apply the what are the area to be placed in device utilization process. The device utilization process mainly used to utilize the lookup table and flip-flop functions, then input output functions in our overall architecture. This is our timing summary. This is a time allocation for 16-bit path delay operation for 25.173 nanoseconds architecture results.